That's my name. My name's Tony Kojundic. Just call me Tony. That's fine. We'll be cool. I know you guys don't have a real dedicated background in concrete, that you're in construction management, so you cover a lot of different aspects. So if for some things I get into in concrete that you don't understand, stop me. But I'm going to try and keep things that you as construction managers are going to run into out there, and the concepts behind it and the logic behind it and those type things. We're talking about high performance concrete, and to start I want to show you a little video here as kind of an introduction to high performance concrete. You may recognize some of the people.
World News Tonight with Peter Jennings continues. Now, solutions.
There are several ways to dramatize tonight's solution. We could tell you that a horizontal asphalt infrastructure anomaly is a curse for millions of American drivers at this time of year. That would be potholes to most of us. We could tell you that $52.5 billion a year goes to highway construction and maintenance, not to mention all the other money to repair the bridges and the other pieces of the nation's infrastructure. It is safe to say, we think, that if the ancient Romans were watching tonight, they would be asking, what took you so long? Here's ABC's Jack Smith.
Roads and pavements, bridges and support columns. All of what's called America's infrastructure is slowly crumbling because what it's made of does not last.
This is ordinary concrete, and this is what happens to it after years of punishment. It falls apart. Most of the concrete in the nation's highways and bridges has a life of just 30 years.
What's the solution? I'm standing on it. Brand new stuff called high-performance concrete. This is a sample. Engineers say this will last not 20 or 30 years, but 100 years, maybe longer. This is what America's roads and bridges could be made of in the future.
Engineers at the New York State Department of Transportation discovered how to make it 2.5 years ago.
We were surprised when we actually did all the calculations and got the test results back and said, my goodness, this really is going to work.
Researchers stumbled on the formula after the Clean Air Act forced power plants to reduce pollution. Huge quantities of industrial waste called fly ash began piling up, collected from smokestacks. At first used as a filler in cement, it turned out to be a key ingredient in strengthening it.
So this is 1/4 industrial waste. But it makes the cement many times tougher.
That's right.
High-performance concrete is 74% cement, 20% fly ash, and 6% microsilica, another type of ash, all mixed with water. When it dries, ordinary cement is actually porous, not solid. That's how salt and water get in. But the fly ash and microsilica are 10 to 100 times finer than talcum powder. And Professor Ken Hover of Cornell has found they literally fill in the microscopic holes in the cement and demonstrates it with colored tennis balls.
So the next thing I would want to do if I want to densify this box is get some mid-sized particles and take those mid-sized ones and try and get them into the box.
They fill in all the smaller voids in between the cement particles, and we just have a very, very dense material.
More waterproof?
Correct.
Stronger?
Yep.
Lasts longer?
Yes.
The new concrete is 3 times more water resistant, 20 times less likely to form cracks, and in pressure tests
9,060 psi.
has proven almost 20% stronger than regular concrete. However, modern scientists were not the first to make high-performance concrete. The ancient Romans were, mixing volcanic ash with their cement to make it far tougher. It's one of the reasons the Colosseum and other Roman buildings have lasted so long.
We really literally reinvented what our ancestors 2,300 years ago had already done.
At least 11 states are following New York's lead. High-performance concrete is more expensive than ordinary concrete, but because it's easier to lay down, costs about the same to use. Engineers say not only could it be an answer to much of America's infrastructure problems, but it could revolutionize all construction. Jack Smith, ABC News, Albany, New York.
That video was actually recorded February 11th, 97, so 6 years ago. They showed a map that only had a few states that have used high-performance concrete on their bridges, As of last year, all 50 states have used high-performance concrete on their bridges to one way, shape, or form or another. New York and Ohio were probably the first two guys to come on board full stream, where the fellow at New York, Don Streeter, was saying that that they had only come up with it back 2 years before 97, which was 95. Reality is they did their first overlays and bridges in the mid-80s. Likewise, Ohio, and then they looked at them, they watched them, they monitored them, they tested them, they looked at them for another 5, 10 years until they really got the data back, which what he was talking about. We looked at the numbers and they're really going to work out. They know they're going to get extra life out of these structures. In those two examples, New York and Ohio, they've been using high-performance concrete, that type of mixed design that Streeter talked about there, since 97 on all of their structures. There's probably 1,000 in both states that have been built, both overlays and new. And I say that because every state is different. What happens in Illinois doesn't necessarily transfer to what happens in Indiana, and likewise New York doesn't affect what happens in Pennsylvania, my home state. I'm ashamed to say that our state has 4 what I would call high-performance concrete bridges. And we've got New York and Ohio right next to us that have thousands. And, you know, the technology just doesn't transfer, which is part of what we do with the Silica Fume Association. As you see in the manuals that you have, the book was published by the SFA and the Federal Highway Administration. We have a contract with the FHWA to help them provide technology transfer to the various states. Since the states don't talk to one another, the feds have to effectively try and you have to take the technology to, you know, Moses. You got to take the mountain to Moses instead of the other way around. If you work for IDOT, you only travel within Illinois. You don't go to Michigan. We don't have any roads in Michigan. Why would you go to Michigan? Even though there's a technical conference in Michigan that you may learn something from, you don't go there, so the technology has to be taken out, which is what we help the FHWA do. The federal government has cut back so much on their field people that now they've reached out to industry like ourselves to help them with the technology transfer. We don't want people to reinvent the wheel. There's no need for a state to put down a bridge deck and watch it for the next 5 to 10 years. The Federal Highway Administration, as we'll see here, recognizes the benefits of using high-performance concrete versus how we built our interstate system the first time. You saw some numbers on there of $52 billion. That was $97. The last the last Congress authorization for funds was $318 billion for all transportation systems. I think like 100 billion of that was for bridges. But today we're going to talk about high-performance concrete in particular. Let me see if we can bring all this up here. Thanks. No problem. Straighten out the projector if you would. What is high-performance concrete? One of the performances we think of is strength, high strength, easy to measure. You make cylinders, you cure them for 28 days, you test them in the laboratory, you know how strong the concrete gets. Normal concrete, sidewalk concrete, highway concrete, 4,000 PSI, 28 days. That's how long it takes for the concrete to change from the mud in order to get hard and develop some strengths. You see a lot of high-strength concrete on high-rise buildings. This is 311 South Wacker. When it was built, it was the tallest concrete building in the world. There's since some other ones. They use high-strength concrete in the columns of the buildings. If you think about it, it stands to reason. If you were to make this column out of 4,000 PSI to support this weight, the column would become very large to support that mass of weight on there, the dead weight. If you make this column 12,000 PSI with a higher modulus of elasticity, the column can become a lot smaller. Not less is the column smaller and you're using less steel, but now if you've got 20 of these columns going up through the whole building top to bottom, and you save 35% square footage on every column times 20, they lease the building based on square footage. So if you can reduce that column size, if there was no columns, Donald Trump would love it because then he could rent out the whole floor. So but the idea is to make the columns as small as possible with as high strength as possible, and then it gives the owner something more to rent, to lease out, and they make more money off of it. High strength in Chicago, 12,000. Right now, Trump Tower is going in at 16,000 PSI concrete. They have a modulus of elasticity. They actually didn't require strength. they required a certain modulus of elasticity out of the concrete so that the building would stay rigid enough. They have an equation where if you live on the top floors, you can't feel the building sway. I think it's like 1 time in 30 years that you should be able to feel the building sway. And they go from that measurement back to how strong the concrete has to be in order to keep the building that rigid in the 200-mile-an-hour winds that they get in Chicago sometimes at those elevations. So it's a crazy calculation, but they're up around 6.6 million modulus of elasticity, which is really high. That's just one property of high-performance concrete. The FHWA says that high-performance concrete is a concrete in which certain characteristics are developed for a particular application and environment. And the operative words there in the sentence being certain characteristics. Concrete can have a lot of different characteristics. High strength is one. Right now, in the construction industry, one of the big things in concrete is art concrete, stenciled concrete. You have some pavements out here that are stenciled to make it look like bricks. It's actually concrete. They throw colors on it. You go to some hotels, they'll have the drive areas to look like specialized stones with colors on it. That's actually a high-performance concrete. They're doing something other than making a gray slab on the floor. They're getting something out of that concrete. Here's a list of what the FHWA says are some of the HPC characteristics. It can be ease of placement. You ever heard of self-consolidating concrete, SCC? That's probably the latest thing in the last 5 or 6 years in the concrete industry. They've got certain chemicals, and silica fume can be used for that application, but they're able to make a concrete that flows like water, but it doesn't separate from the aggregate. The aggregate and the mortar and everything moves in unison. So, you know, normally, anybody work with concrete? By hand, actually wheelbarrowing it and putting it in, or what type of work? Actual finishing? Okay. You know how heavy it is to pull the concrete around. You know, it's back-breaking work to do. SCC concrete, particularly in a precast plant, where they're filling up concrete in forms, or even in houses where they're filling up basement walls. SCC concrete, they can place it at one end of the form and let it flow like water to the other end of the form, and the aggregate will stay with the leading edge of the flow. In a precast plant, they've cut labor, you know, probably 80% in the last 6 years. They don't have to vibrate the beams, and they get much better finishes on their concrete. But that's just one area of what would be a characteristic for a performance. Early age strength, if we wanted to fast track, if we wanted to rebuild an intersection, we wanted to get on it and off of it in 4 hours' time, you can do that. There's concretes that you can tweak that characteristic and make it happen. The idea here is to make engineers think, when we talk about performance, to have them begin to think that there's more that you can do to concrete besides just achieve strength. Strength is just where everybody's head has been for the last 100 years or so. You know, if a little bit is good, a lot has to be better. But there's other things that make concrete fail, not just strength. In this case, we're looking at a stilling basin of a dam that we'll show a little video on here, that the concrete obviously was eroded away by abrasion erosion. That needs a concrete that has extra toughness. That's a performance that you need that can be improved. If you're making containment vessels for low-level radioactive, this is Hanford nuclear site in Richland, Washington, 12-foot thick slab or walls of concrete here. They're worried about heat of hydration. When concrete gets hard, changing from its wet state to a hard state, it generates heat as part of the chemical reaction. And in that big mass of concrete, in big thick walls like that, concrete can get pretty hot. If you have a core differential temperature from inside that slab to the outside of the slab that's greater than 36 degrees F, it'll crack. Well, you know, obviously they don't want this to crack because it's supposed to last a couple hundred years and containing radioactive material. So they want it to be very volume stable and low heat of hydration. They don't want to generate a lot of heat. They want the concrete still to get hard and last for a couple hundred years, but they don't want it to hit 160 degrees when the outside environment's 50. So there's things that they can do to the concrete to make that work. It's not just driveway concrete, or to make longer life. That's where the FHWA spends most of their focus on, how we get our bridges, as we heard in the video, to last longer. The last inventory in 2005 said we had just short of 600,000 bridges in the United States, these aren't culverts. I'm trying to think of the definition. They had a certain length that would actually make it a bridge. It's not just the culverts over the little creeks. It's a physical bridge. Of those 595,000, there's about 28% that are rated deficient. Deficient either because they're under capacity, structurally deficient, falling down. This bridge right here is in that category. There's a lot of Erie bridges like that in Pennsylvania, not just at Erie. But in Illinois, we're down to 18%. The national average, remember, is 28%. So Illinois has done a great job in the last 10 years of cutting that number down, because the original number, this thing was up around 240,000 10 years ago. A lot of states have done a good job at knocking the number down, and Illinois is one of them. Illinois has been using high-performance concrete. The first overlay was placed here in 1986. State Route 4 crossing I-55 is the overlay. It's still in place. They only expected the overlay to last 10 years, and we're up to, what, since 86? 20 years. So they doubled the life out of that overlay. An overlay was put on the bridge because the bridge was rated as deficient. Most of the bridges fail because of chloride attack through the surface of the bridge, getting into concrete, which acts like a sponge, sucks up the water, sucks up the chlorides. Once you get enough chlorides into the concrete at the layer where the steel is, that's corrosion is actually an electrochemical reaction that you need an electrolyte to carry the current through the concrete. And it's the chlorides, the negatively charged chlorides in the concrete that act as that current. A little bit beyond ourselves here. But the idea of an overlay is to repair, to get extra life out of a bridge that they would normally have tore down to put up a new one. So in Illinois' case, they got twice the life out of it instead of having to tear it down and start over again. We see a lot on parking garages, not just bridge decks. Parking garages are probably even more frightening because most of their decks are very, very thin. Most of their decks have post-tensioning cable in it. You see cables are all under tension and they're jackhammering out concrete because of corrosion and failure. This happens to be underneath the Amoco building in Chicago, which it's one of the 3 tallest buildings in Chicago. It's like 105 stories, and we're 6 stories underground jackhammering out the foundation. What's wrong with this picture? You know, we're taking out the foundation of a 105-story building above us. So this was made with conventional concrete. The chlorides were brought in by cars driving on the highways. They park underground in a warm building. The moisture and everything falls off the vehicles. They're underneath the building. There's no way for them to come out. They're there forever. They get into the concrete. Whatever gets deposited there stays there. So parking garages under buildings are notorious for this type of problem just because they're trapped. Whatever gets in there doesn't get out. Outside parking garages, yeah. Yes, I think it's actually like 8 or 10. No. That's cool. But what does service life mean on something like a parking deck or a bridge? This is a famous way of depicting it from Professor Tootie back in '82. Concrete acts as a sponge. That's this initiation period here, where it's allowing chlorides and carbonation to actually penetrate and get into the concrete. There's no corrosion happening at that point in time. It takes a certain amount of electrolyte in the concrete to start corrosion. That's where we see the corrosion starts here, and then as it corrodes, when steel corrodes, it effervesces and swells. It swells to 4 times its normal size. And although concrete's real strong under compression, it's real weak under tension. And the expansion of rusting steel is a lot of force when it swells up to 4 times its size. That causes the concrete to break. Once the concrete breaks, more water gets in, more corrosion, freeze thaw. You get potholes happen very quickly. That's the propagation period. The one bridge that had the sign of Erie pointing to it obviously was in this part of the structure, or was in this part of the equation of its service life, way beyond the initiation phase. But when do you pull the plug on a bridge? When do you say it's done? Well, that one's done. That happened a month ago. About 20 miles from my house, crossing Interstate 70. Luckily, no one was hurt. It's imagined that no one was hurt on this. The bridge is 40 years old. The reinforcement was completely rusted through. It's on the shoulder. You know, so all the salts and all the waters and everything are going to run to the side of the edge of the bridge where the gutters are. That's where the salts and everything got in. They lost all the steel there. There was no traffic on this at all. It fell down under its own weight. This building was rated deficient. It was scheduled to be repaired. Well, it is now. But there's 2 other bridges that were made all at the same time on either side of this one. PennDOT has since shut down both of those. And I think last week they actually blew up this one. So, I mean, you know, some states learn by, you know, taking it out of service before this happens. Sometimes the end of service life can be pretty dramatic.
This was a rough radio kind of thing?
Without the steel in the concrete, concrete is very brittle. It'll break like a pencil. That's why you have reinforcing steel in concrete. Steel's real good in tension. Concrete's real bad in tension. So if you put those two together, you got the good, you know, you got them both working together. But obviously the steel in this case was completely corroded through, so that it was acting like a pencil. The weight, just the weight of the bridge itself, the concrete couldn't carry it without the steel.
So overnight happened just
Yeah. Yeah, it was like 5 in the morning when it went down. This happens in parking garages all the time. Bridges are more catastrophic because of their potential, but Minneapolis is famous for having parking garages fall down for the exact same reason, that the salts just corrode through the reinforcing steel and there's nothing left holding up the structure other than a concrete pretzel, and the pretzel snaps.
That was in Pennsylvania, you said?
Yeah, Interstate 70, just south of Pittsburgh. How do we make high-performance concrete? Well, concrete, real simple, is 2 ingredients. It's glue and it's the aggregate. The aggregate is your sand and your rock. Normally that's something that happens locally, that you're going to get out of the ground locally, and normally it's the best material that you have in your concrete. If you think real pragmatically about what happens with concrete, people complain about it cracks. It has carbonation, it has conductance, it takes in chlorides, it scales, it has creep, it has delayed etrichnite. All these bad things happen to the mortar, except for alkali silica reaction, which could happen from your aggregate, but that's something we know how to take care of. That's normally the aggregates are the best things you have. So, you know, you're dealing with mortar here and you're dealing with aggregate. Those are the 2 things you're going to put in concrete. These cause you a lot of problems if you don't do it right. This is the good stuff in the concrete. So real pragmatically, I want to use more aggregate and I want to use the least amount of cement that I have. I want to make it the best glue that I can possibly make it, but I don't want to use a lot of it because a lot of it gets me into trouble. That statement alone that I just made to you is almost 180 degrees different than what everybody thought in the last 50 years in the concrete industry. You got a problem with your concrete, put more cement in it. No. If you add water to these 3 things, slag, Portland cement, Class C fly ash, they hydrate. What that means is they react. Chemically, they react with the water and become something different. Like baking a cake, you put flour and milk together and sugar and you bake it, it becomes something different. Well, likewise, when you put cement with water together, the cement starts reacting with the water and it starts growing crystals and the crystals interlac, and that's what makes the strength. Slag does the same thing, Class C fly ash does the same thing also. They hydrate. Silica fume, or I wish I had a Class F fly ash picture here, but I don't. If you add those 2 things to water, all you made is dirty water. They don't hydrate. But if you remember that video, the fellow in New York was talking about this Roman technology where they used ash from Vesuvius. And what they actually did is they ground it up with a local limestone from Pozzolana, Italy. And when they put those 2 things together, this silica, which is in F-ash and silica fume, reacts with lime and actually makes concrete. It actually gets hard. It gets hard pretty good too, if you think of the Appian Way and the Colosseum and all these other buildings that are still up there. So we've got a technology here, this pozzolana chemistry, and that's really what it's called. It's called pozzolanic chemistry now. This idea of lime reacting with silica, amorphous silica, that's been around for a couple thousand years. Portland cement was patented in 1824, less than 200 years ago. So we only have 200 years of history of working with cement, this type of cement. It's called Portland cement because the color resembled the rocks that they found on the Isle of Portland, which is an island off of England. It has nothing to do with Maine or Oregon, or has to do with that island. But if we put these materials together, we can have some good things happen. If we combine this Portland cement chemistry with this pozzolanic chemistry, we can make a really good glue for our concretes. Even though all those materials look like powders, there's some difference in those materials. Slag, fly ash, two different types of cement, they all basically have the same particle size distribution. If you look at the D50, 50% of the particles, the D50 is probably about what, 12 micron, 13 micron, somewhere out there, 10 to 12 micron. The D50 of silica fume ends up being about 0.1 micron. Very, very fine material, 100 times finer than cement grains. What it is, he's asleep, I was going to throw it to him, but here you go. That's actually silica fume. That's a full container of silica fume. If you think of the word silica fume, fume in Latin means, anybody? Close. No fumada. In a restaurant bathroom, no fumada. No smoke. Fume is smoke in Latin, or French, Italian. And it actually is silica smoke. That's captured smoke. You can open up the container and look at it, it's fine. It won't jump out, it won't float away. You throw it in the air, half of it will probably stay in the air, but the material as it's captured, this smoke weighs about 8 pounds a cubic foot. Water weighs 62.4. This weighs 8. It's captured smoke, literally. The plants used to look like this. Obviously this is taken out of the user's manual that you have in front of you. Should probably say something about the user's manual first. That's written for producers and practitioners of concrete. It's written for ready-mix producers, it's written for contractors. It's not an engineering document, it's a real how-to. The first couple chapters deal with the background, like this is actually in chapter 1. What is silica fume? Where it comes from? All those things that we're going to cover here real quickly. Latter parts of the book, chapter 6 deals with mix designs and proportioning. Chapter 8 deals with contractor issues of placing and finishing. So it's all written, the FHWA wanted a document. We have enough engineering documents on high performance concrete. We needed something to take from that industry back to the people that actually have to build with it and teach those people how to build with high performance concrete. That's what this manual is dedicated to. I think it's perfect for what you guys are headed for.
If you put 1 spoon of this material in a cup of water, what will happen?
You'll have dirty water. You can actually mix it in with water. The one video that we'll see on the dam that's being repaired, the way of introducing that into the concrete was actually in a liquid form where they suspended the silica fume in 50-50 in liquid versus trying to handle it in a dry form. That was before they figured out how to handle a material that light in a dry form. What they found was, and I thought this was pretty unique too, they put that material in a big silo about 6 stories high and blow a lot of air, very low pressure, but about 700 CFM of air through the bottom of this silo. If you stand at the top of the silo and look down on the top of it, it looks like the whole thing's boiling. It's just all kind of air coming up through the silo. What happens is when the air goes through this column of silica fume, it causes those little particles to collide. And because of van der Waals forces, the attractions of fine particles, they actually start sticking together. And so we can actually increase the bulk density of the silica fume from 8 pounds a cubic foot up to about 40. And once it gets up to 40, then they can haul it around and put it in trucks and blow it into silos and treat it like cement and fly ash and treat it like any other material and handle it. Can't handle it when it's 8 pounds a cubic foot. When you get up to about 40, you can handle it with that way. But I think it's strange because normally, if even like flour or something, if you want to fluff it and make it lighter, you blow air in it. Right? And it fluffs everything back up again, just like shaking that up in a container, you'd fluff it all up again. But if you do that long enough, if you fluff it long enough, it starts getting heavier, which I think is a neat trick. But anyhow, this is a schematic of the plant that produces silica fume. What they're doing at point A is they're putting in quartz, big rocks about the size of your fist, almost pure white. Quartz, coal, wood chips, and coke, and ignite it all in an open arc electric furnace. The electrodes anywhere from 24 to 30 megawatt electrodes. You walk into a furnace building, I swear you can feel the stray electrical current in the air. It's so powerful. But what they're doing is they're melting the quartz. And they're melting the quartz to extract silicon, element number 14 on the periodic chart, Si. That's a chunk of it here that we'll pass around. The only thing you make out of silicon is silicones. Dow Corning and GE, they take that element and run it through their reactors and turn it into silicones. Bathtub caulkings is what everybody comes to mind. Glues, it's used in dashboards, it's used in plastics, it's used in shaving cream, it's used in deodorants, it's used in cereal boxes, fake breasts, it's used in anything that has silicone in it starts out as that rock, is that element right there, element number 14. That's what comes out of the bottom of the furnace after it's tapped. The smoke, as you saw, used to go up the stack 50 years ago. Now they pull it down with fans and run it through a series of filters. After it comes out of the filters, it weighs what you have in that container. The densification silos that I talked about happen afterwards. But that's pretty much where it's produced. This is what it looks like coming out of the ladle. The hot silicon metal is poured into chills. That's exactly what it does in these big flat slabs, is chill. And then they drop it on the ground. It shatters like glass. That starts the crushing process. They crush it to that size, and they'll take it even further. They'll take it from that size all the way down to 10 micron in size, which is pretty damn fine. They use that in ceramics. This is actually, as you said, the silicon metal coming off, or the silicon. This is the silica fume, the silica fume going up the stack. As it comes off the silicon, it's all gas, SiO, gas. When it hits about 600C, it combines with another oxygen and forms an SiO2 solid. So you get this precipitation from a vapor to a solid, like a formation of a rain droplet. Is how the material ends up being so fine. Remember, we said it was 100 times finer than cement grains. It's captured smoke is what it comes down to. Yeah, that's a question that always comes up because of the name silica, and maybe these next couple slides show it better. This is another example of trying to give a perspective of what we're talking about here. If a cement grain, one little piece of powder of cement, were the size of the Washington Monument, silica fume would be the size of a 6-foot guy. That's the difference in size. On a typical mix, if you're using, and they normally use 5–10% silica fume cement replacement, if you're using that much, the calculated number is about 2 million pieces of silica fume for every cement grain, which I think is what it says down here. No, must be the next one. When this material is formed into a solid from this vapor, this is a real close-up of what the material looks like. Little glassy spheres. I had somebody look at this, some researcher looked at this, and they didn't know what it was. They were calling these, what did they call them? Oh, they call them Death Stars. Because of the, obviously the way it's formed. But because they're amorphous, amorphous means non-crystalline. And crystalline silica is what produces silicosis. Crystalline silica is what you'll find in the beach. The sand, the dust that's blowing off the beach, since you're getting ready for spring break here. Don't lay on the beach too much, you'll get silicosis. How's that? But that's crystalline silica. Crystalline silica, when you find powder, you'll breathe in, it'll get hung up in your aerols, in your lung sacs, and that's the start of silicosis. Where this material round is considered respirable, you breathe it in, you breathe it out, it doesn't get hung up in your lungs. It's one of the cleanest things in a ready mix yard, safest things. People don't think so because it has the name silica, but they keep thinking it's crystalline silica and it produces silicosis. You have to tell them all the time, you use silica in your plant, in your sands all the time. You put sands in your concrete all the time. Sand doesn't react with cement water, does it? You can cut open concrete 10 years later, look at it under a microscope, the sand's still there. You put silica fume in with cement, 7 days later, you cut it open, look at it under a microscope, you won't find any of the silica fume because it's reacted. Amorphous silica reacts, crystalline silica does not. Even though there's silica in the title, they're two separate materials. This is another shot of trying to show the particle packing theory. Dr. Hover on the video was talking about fitting in these little balls between other balls, and this is a shot of actually a cement grain. One cement grain here and one cement grain here, 1 micron scale, and that's silica fume particles mixed in within. I always use the example of if you can visualize filling up a barrel full of baseballs, you can only get those baseballs so close together, and you have void spaces between all the baseballs. Capillary pores in concrete, just like regular concrete. If you mix yes.
But just in a relative scale, how big would like a water molecule will be, or the chloride molecule be fit in between there?
In the chloride's case, it's in a dissolved state in water. And really you're talking about
I guess I don't really ask, would there still be some penetration?
Yeah. Right. Because you've put something between those baseballs. Otherwise, you could pour water through it pretty easily, just physically blocking the pores. That's what the ceramic people do in their particle packing theory. Their theory is if they get all the particles graded just so that if you squeeze them all together, there's no room. It's 100% dense. That's why you get some little ceramic parts you put in your hand. They're this size and they weigh 3 pounds. They're just so densely packed together of particles. And that's what we're trying to do with concrete. If you think about it, that's what we do on the aggregate side. We start off with big aggregate. We mix in a gradation of aggregates and then a gradation of sand so that when you put all those things together, they fit together very nicely so that you can use very little cement, very little glue. So all we're doing now, instead of grading the aggregate, we're grading the powders. We're grading the mortars. We're finding something to fit in that finest fraction between the cement grains. But you still will have some permeability, yes. Yeah, it's not waterproofing. It's not waterproofing. Your example, you're still getting a little bit through. Less permeable, though, compared to if you did nothing. And what... What's the difference? No, the rock that you have, the silicon, the elemental silicon is just Si. The silica fume is SiO2 amorphous. So there's not, they're two different animals. They're two different animals. The silicon that you have there is, when it comes out of the furnace, is about 3 nines pure, 99.9% pure. If you want to make, silicon chips or photovoltaic cells or something like that, you've got to push it up to 5 or 6 nines pure. They'll take that rock and do further things to it to drive out more of the impurities so that they can make silicon chips and wafers and those type things. But it all starts out as that material. Yeah, all starts out as that material. The fume is the waste material. That's the pollution that used to float in the atmosphere and people used to have to sweep off their steps. As they're saying here, that the common thought was before the use of pozzolanic materials for particle packing, that the best you could do was lower the water-cement ratio. Use the least amount of a lower water-cement ratio, you have a lower permeable concrete. So that was always the trend, that if you wanted low permeable concrete, you made low water-cement ratio concrete. And what the next slide shows is that's not necessarily the case, or there is ways, it is the case. You do get a lower permeable concrete at a 3.5 is pretty low, but by adding a portion of silica fume or replacing the cement with even 7% silica fume, you can get somewhere around 60 to 80% reduction in permeability, even at a real low water cement ratio concrete. All those different values there, 120D, those are all different permeability tests that people run on concrete. And this is just a way of comparing all these different test methods, showing, they more or less show the same thing, the same type of trends. So it takes very little of this particle packing to get the biggest impact. As you see, you have a point of diminishing return here at about 7%. From here on out, as a cement replacement, you're only producing strength. If strength is your goal in a high-rise building, you may be up there at that dosage. If you're doing a parking garage or a bridge deck, you probably don't need strength. You're looking for this, though. You're looking for a reduction in permeability to keep the chlorides out. Or a loading dock or an industrial floor or a chemical plant or a sewage treatment plant or anywhere where you have an aggressive chemical that's going to get into the concrete, because all concrete is a sponge.
You're looking for durability in that case.
Yes. They have, there's, at one count, and it was a couple of years old already, but there were 200 different companies in the United States that sold chemicals for sealing concrete. Everything from Thompson's water seal to some pretty sophisticated stuff that 3M makes. But there's 200 different people that make chemicals to seal the surface of concrete, to make it last longer. If any worked, wouldn't it put somebody out of business? But what happened is they all fail in time. They all traffic off. They fail either because of wheel traffic or because of UV traffic or freeze thaw or something. And they're all superficial treatments, where what we're talking about here is actually making the concrete. You're making the concrete when you have a chance to do it right the first time. You can make it real low and permeable from the get-go. And longer life. That's exactly what they're trying to do. One way of looking at this is a life cycle model. This Life 365 model is software that we helped pay for with Grace and Master Builders. It's actually an ACI document. ACI 365 is the committee that deals with predicting service life. And what this model has or allows you to do is build a structure and put it in a various part of the United States, build it with different types of concrete, turn the crank and it'll tell you how long it'll last and how much it costed to last that long. Show you how that works. Real basically, it gives you a procedure where you can design a deck. In this case, I use the example of the Illinois Tollway 294. They have 8-inch thick slabs. They have 4% steel. Volume of steel is 4%. They've got 2 inches of clear cover over their concrete. What this model allows you to do is build a couple different cases. I tried to keep it simple and just use the base case and the high-performance concrete that they are using. You could have 30 different cases if you wanted. The model knows the surface chloride chemistry for, in this case, Chicago. I didn't have one for Charleston. The nearest other place, I think, was Springfield, so I picked on Chicago instead. But it also has the temperature history per year, so it knows how much salt is going to hit that bridge. In this case, we said we want our bridges to last for 50 years. In this particular case, that was the design life. The one video we saw from New York, they said the original interstate system, when they started it in 1956, the average bridge lasted 35 years, which was great. When they started building the interstate system, they didn't have 18-wheelers. They didn't have 80,000-pound trucks running down the highway pushing over 100,000 now. And they didn't have as many that were on the highway. And they probably had maybe 2% of the 18-wheelers back then in 1956. You didn't have the highways to carry them. So the highways you had were the windy 2-lane roads. You didn't put the big trucks on them because they weren't feasible. So there wasn't any 18-wheelers back then. So to have those bridges, even though they tried to design them with as much safety factors they could put into these bridges, the guys that designed the interstate system, they had some idea of what impact it was going to have on our economy, but it was only about half of the impact that it actually had on our economy. And now we know that if we do it right now we have a second chance to redo our bridges. We have a chance to make them last 50, 60, 75 years. They won't last forever, but they'll last more than what we got out of them the first time. And this is what this model tries to show here. The basic mix design, water cement ratio, we actually can put in some dollars in this case to see what the model looks like when we run the exercise on this. Yard of concrete up in Chicago, that's probably light. It's probably closer to 150, 150, but I put 120 bucks. The model knows for this water cement ratio concrete, there's a certain diffusion coefficient built into that concrete. It has a certain permeability. That's the permeability number. It takes a certain amount of chloride concentration at the steel, 2 pounds per cubic yard, to start corrosion. So we've got to get 2 pounds of salt per cubic yard down to the steel in order to start corrosion. We're going to put epoxy coated bar on epoxy coating on our steel to try and make the steel from corroding. We said it's an electrochemical reaction. All epoxy coating is rubber coating this wire. You're coating the steel with a layer of non-conductive material to try and keep electrical current from hitting that rebar, that steel. That's all it does. It'll still start corroding when you get to 2 pounds per cubic yard of chlorides, but it'll corrode at a much slower rate. Gray steel without epoxy coating will have a propagation of only about 6 years before the structures, really fall apart bad. But epoxy bars will buy you about 20 years of life in that propagation part of the model. We had that initiation part and the propagation part. it's buying us extra time in that propagation part. The high performance concrete, we use the same water cement ratio, a little bit extra higher cost. We put silica fume and fly ash in it, had a big effect on the diffusion coefficient. We're still going to corrode at the same amount of chlorides if we can get them in there. And we're using epoxy bar. As I said, this is what they're actually doing up at 294. When we turn the crank on this model, it says that the base case is going to achieve our 2 pounds of chloride in 6 years, 8 years of normal use. Normal use in that area is that they throw, and I used to have a bag, 6 pounds of salt per square foot per winter. That's how much the DOT figures they actually throw on the 294 bridges. In the course of a whole winter, 6 pounds of salt end up on every square foot of bridge that they have on 294 over the course of winter. That's a lot. In the case of the high performance concrete, to get that same 0.2 factor, we're out here 20-some years, 24 years plus. If we turn the crank on this and actually run the economic model, we see that going in place, the initial cost, the high performance is a little bit expensive according to our model, but easily if we have a corrosion that's not going to happen until 27 years versus 7 years, and we put epoxy on top of it, we're going to last the 47 years before we have to repair that bridge versus half as much, versus 27, according to this particular model. We could tweak it, we could do other things, we could make this bridge last 100 years. We could use more cover, we could toughen up the mix, we could do various things for it. In this case, the goal was 50 years, which is what they achieved. That's what they wanted to afford. They're not worried so much about this thing lasting 100 years. This is in Chicago. They know they're going to overcapacity it before they get to 50 years. They just want it to last that long so that it doesn't fall down. They'd rather it be obsolete because of capacity, not able to carry all the vehicles that they're going to be driving around up there in 50 years, but to have it last without repairs. Okay on this? Make sense a little bit? In the manual here, we said this manual, as y'all can read, is not for engineers. It's for contractors and the people in the field actually doing the work. Silica fume and this type of technology, you know, we heard it said that it's been around for a couple of thousand years, and it's been in this country since the mid-70s. I've been doing it since the early 80s, but there's still a large group in the construction industry that it hasn't really embraced high performance yet. And sorry to say, it's the people that actually have to do the work. The engineers and the designers and the owners and the FHWA and the DOT and everybody else, they know what this can do. As they said 9 years ago, we know the numbers work, the models work. Now we have to get people to do the right things. It's a little bit different than regular concrete. We've seen some of the differences here in particle packing and those type aspects. What does that mean to the constructor? What does that mean to a ready mixer? What does he have to do differently with the way he's been doing business for the last 30 years? How does that change his life? That's all covered in this manual. That's a real how-to. It's written to that audience. It tells you how to set up your batch plants. If you're proportioning concrete, there's a very long, elaborate, formal engineering way of doing mix designs. Or if you have a good mix design that you know has already worked, use that as a starting point and just tweak it into your own. Again, technology transfer. Don't reinvent the wheel if you know you already have structures. In this case, table 6.2 in the manual is actually 2 pages worth of mix designs that across the top here gives you where it was used. A high-rise building, columns. Another high-rise building. A bridge mix in New York DOT. It's actually the mix that was on the video. A shotcrete mix. You want to use silica fume shotcrete. Here's a starting point of a mix design. The Hanford nuclear site, low heat of hydration, those mix designs. There's parking garages and a couple other mixes. Those are all starting points so that you don't have to reinvent the wheel. Because this is an FHWA publication, that table's all in kilograms per cubic meter. But if you go to the back of the book in the appendix, all the tables are in pounds per cubic yard. They're all in our language.
These recipes are public domain?
The mix designs? Yes.
Kind of recipes, just don't do it?
These are mixed designs that have been published in technical papers. All of these structures that are listed here have all been, documented and discussed and studied. And so yes, the mixed designs are all in public domain. They're only starting points because you have to incorporate your own aggregates. And your own aggregates, the sands are going to be different, the limestones or gravels are going to be different. You have to tweak your mix design for your own materials anyhow. These are just starting points so that we don't have to start over from those very laborious engineering practices of coming up with a mix design. We already have good ones. Let's start with these and just tweak them. And how we tweak them is they have, the book goes through a step-by-step procedure. I think there's 6 different steps here of how to take one of those mixed designs and turn it into your own. Again, I said it's written, it's real practical. Producing it at a ready mix plant, there's a chapter on chapter 7 here. Setting up silos to handle silica fume is a little bit different. We saw the material is obviously lighter. We found out that there's another property to the material that is pretty unique. It has an electrical charge, not an electrical charge, more magnetic charge, that happens to be at the opposite end of the spectrum as steel. So if these pipes, from blowing it from a truck and blowing it into a silo, blowing it through these small confined spaces, we found that if you blow it through steel, it has a tendency to want to stick to the walls just from this magnetic attraction. And once it starts sticking, it just builds up on there. But they found that by using rubber and silica fume are at the same end of the magnetic spectrum. So it's like 2 negative poles repelling each other. You can blow it through rubber all day long and never packs up on it. So one of the little tricks here setting up a plant for handling this material is the guys have to get rid of their steel pipes. Their rubber works better. The material is also used in bags. Some of these bags are actually repulpable, which is what they're doing here, that allow you to just dump the whole bag into the concrete truck. The paper is designed to actually shred up with the aggregate, to beat it up and actually dissolve back into cellulose fibers. Doesn't dissolve, it repulps. The aggregate beats the paper back into its cellulose fibers. And it doesn't work on all mixes. If you're dealing with overlay mixes where the aggregate is real small, 1/2-inch aggregate, pea gravel, number 8s, those type things, the aggregate's probably not, in the mixture, is probably not impacting the paper enough to really do the shredding. So the manual goes into great detail of what mix designs these bags can be thrown in on, or some mix designs where we're doing overlays where there's real, you may have to dump the contents into the back of the mixer. But it comes in bag form, it comes in bulk form. The major work that's going up in Chicago and all the high-rise buildings, they work with it out of silos. The Interstate 70 here, as it crosses the border from Indiana into Illinois, those bridges were all repaired with this concrete in 03, 02. That was actually done with bags because bridges use a little bit less volume of concrete than a big high-rise would. So it comes in different forms, but the manual will go into detail step by step of how to do it right. Some of the sexy applications for silica fume concrete, and this is under construction right now. This is actually an artist rendition of the Hoover Dam and a bridge that they're building below the Hoover Dam. I don't know if anybody's ever taken a tour. Anybody taken a tour of the Hoover Dam outside Vegas? There you go. This road comes down State Route 92 and weaves its way back up this side, goes right across the top of the dam. And the visitor center's over here, and the parking garage is here, and people were on this highway, and the tour lets out here, and people were on this highway. There's 18-wheelers that cross this. It's like driving 18-wheelers through recess in a schoolyard. I mean, there's people all over this bridge all day long taking a tour, and they've got to snake down this canyon and across it and back up the other side at about 15 miles an hour. Plus, now the 9/11 terrorist threat. The idea is to get all that traffic off the bridge, not just for safety reasons, but for terrorist reasons. This bridge has been designed for 30 years. After 9/11, it's being built real quick. The columns in that bridge, another artist rendition, the box beam here and the concrete going up to this is going to be a steel bridge here with asphalt decking, but all of this concrete here is all silica fume concrete, all 10,000 psi, actually 12,000 psi silica fume concrete. There's another artist rendition of it. They've gone to great lengths because of where it is, and it's going to be photographed quite a bit to try and make it blend with the surroundings as much as they could. That's probably over-exaggerated. The website here is pretty cool. You can actually drive across this bridge on the website, what the surrounding is going to look like. You know, it's a 3D model of what the bridge driving across will look like. I need to start the other tape, if we may. Questions? Anything?
Technology Company presents the story of MSAC microsilica additives and the concrete used to repair the Kinsu Dam's spilling basin. This ultra-high-strength flowing concrete was used to repair the stilling basin at the Kinsu Dam here in the Allegheny Valley in northern Pennsylvania in October and November 1983.
I'm Mark Luther. I'm a project engineer for Elborg Technology Company. We're working on this project. It's repair of the stilling basin of the Kinsu Dam.
The U.S. Army Corps of Engineers is the federal agency responsible for maintaining the nation's waterways. The Kinsu Dam and its stilling basin is one of its responsibilities. A stilling basin is exactly what its name implies. It stills the water that flows out of a dam before it reaches the main channel of a river or other body of water. If there were no stilling basin, the energy from the high-velocity water would simply gouge out great holes in the riverbed and its banks and possibly endanger the stability of the dam. At Kinsu, the stilling basin is a large area, about 204 feet wide by 180 feet long, with 5-foot thick slabs of concrete. It was originally placed in operation in 1966 and was made of good quality concrete with 6-inch sized aggregates. By 1973, the combination of high-velocity water flow and the presence of debris in the basin had eroded the concrete surface and caused general erosion, with holes as much as 3 feet deep. That same year, the U.S. Army Corps of Engineers let a contract to repair the entire slab with a 1-foot minimum overlay of low-slump steel fiber reinforced concrete, the very best concrete then known for this type of repair work. 9 years later, in 1982, underwater inspections by divers showed that in some places, the 1-foot overlay of steel fiber reinforced concrete had been worn away, and as much as 2 feet of the original slab was also gone.
And then over here you see the worst damage. This is where the greatest force from the upper sluice gate number 2, occurs. This is where the water impacts and swirls around and the energy is killed. And as you can see, it's really done a number on the concrete here. Some of these holes are 2.5, 3 feet deep, if not more than that. Well, as you can see, the fellow with the Philadelphia rod there, I don't know if you can see how deep he is there, but I would say where he's standing right there is over 2 feet deep right now. And what they're doing is taking elevations, using that rod and the level behind us here to determine where the level of this concrete is now so they can determine what they need to do.
In order to more effectively repair the Kinsu Dam stilling basin, the Corps of Engineers initiated extensive abrasion erosion testing at its Waterways Experiment Station in Vicksburg, Mississippi. It wanted to determine which materials are able to stand up to high-velocity water, often containing rocks and boulders from the riverbed. Lab tests of concrete produced with MSAC microsilica additives found it to have an abrasion erosion resistance suited for the Kinsu repairs. Through the use of MSAC microsilica additives, it was possible to obtain a strength and denseness that made concrete far more resistant to abrasion than any concrete produced in the United States before. It has long been known that the strength of concrete will increase dramatically if we were able to fill its pores with a cementitious binder. Concrete with MSAC additives achieves its extreme resistance to abrasion through its ultra-high strength and virtual impermeability. With MSAC additive, it is possible to create these properties and still maintain a flowing and self-leveling concrete. But first, the Corps of Engineers required field tests at its Neville Island facility in Pittsburgh, using a ready-mix concrete plant operation to prove this concrete could be produced and placed satisfactorily under normal day-to-day working conditions. 3 different concrete mixes with 3 different blends of MSAC additives were batched and shipped from a transit mix plant in the Pittsburgh area. The concrete was rapidly placed and finished. Slumps were as high as 10 inches, giving a flowing consistency for easy handling and placement. Membrane curing compound was applied immediately after the final finishing operation. At Neville Island, concrete containing MSAC additives tested over 10,000 pounds per square inch at 7 days and over 17,000 pounds per square inch at 90 days. In its specification for the Kinsu Dam Stilling Basin rehabilitation, the U.S. Army Corps of Engineers required the concrete to attain compressive strength of 10,000 psi at 7 days and 12,500 psi at 28 days. Slump was required to be from 7 to 10 inches. The contractor is Casey Company of Pittsburgh, Pennsylvania. The concrete was produced by Harmon Brothers Ready Mix Concrete Company in Warren, Pennsylvania.
I can't think of anywhere else in the United States today where they're pumping 10-inch concrete and getting 16,000 psi unconfined compression test results in 28 days. That's what we're doing here. That's one sample we have received. The average is closer to 13,000 psi in 28 days. But you have to keep in mind, this is flowing concrete. Typically, it's a 10-inch slump. This is Harmon Brothers concrete plant where the 2,000 cubic yards of microsilica concrete will be made for the dam. This site is about 8 miles from the dam. Behind me is the plant where the concrete will be made. One of the advantages of MSAC concrete is you can make it in an ordinary concrete plant, which this is. No special modifications were made to this plant to enable us to make a very high-strength concrete.
Here is Alborg's mobile dispensing unit, used for batching MSAC into the truck mixer preloaded with concrete. The MSAC and the concrete were mixed in the truck before the truck left for the dam. Concrete will discharge into the remix hopper of the concrete pumping machine. From there, the concrete is transported down to the formwork, where the concrete is placed into the slabs, and there it is put in place. This is just one way to transport concrete. They had thought about using buckets. They decided on this job to go with the pump because they get better control and it goes a little faster. Our particular concrete seems to pump very well. Where the remix hopper is, samples are taken from the concrete, and these samples are tested to make sure the concrete has the proper consistency. Had maintained its ability to flow and to level itself after 8 miles of trucking from the ready mix station. A curing compound is put on to seal the water into the concrete so we get efficient hydration. After the concrete has been put in place, the basin will again be filled with water. And we expect our materials to last twice as long as anything that has been used so far.
That dam, if you follow the timeline for the structure, it was built in '66. It lasted for 6 years, and then they put steel fiber reinforced concrete in for repair. The steel fiber reinforced concrete then lasted 9 years, up until 1982. In 1983, they went down and did this repair in 1983. The divers have gone down. They used to go down pretty regularly, but they've even stopped going down now. They're up to 23 years now. They expected, you heard them say, they expected for it to last twice as long. They were hoping to get 10 years, 20 years out of it, and they're already up to 23, and they don't even go down and look at it anymore. It's just performing that well. What they found is the mechanism for failure in most abrasion erosion, or in most abrasion, is that even with wheel traffic, is what happens is the weak link of the concrete breaks down first. And normally the weak link of the concrete is the mortar, is the glue, is the cement part that holds everything in place. And after you lost enough of that bond, then the aggregate comes free. And the aggregate comes free and it gets ground in and more stuff loose. So it's really the loss of the weak link first that causes the abrasion erosion, because then everything happens after that. The idea of making the mortar stronger is to make it so that there is no weak link. Make the mortar as strong as the aggregate so that everything abrades at the same rate. You see a lot of industrial floors that in the past they used to place a normal concrete and the contractor would come out and throw a shake. They called it a shake. You throw a hard aggregate on the floor. Sometimes they were actually iron aggregates, and actually try and work that into the concrete surface for more abrasion resistant surface. And that's all well and good. You put a really abrasive resistant aggregate in 4,000 psi mortar. And the mortar breaks down first, the aggregate comes free. You've got, you haven't changed the weak link. You've made your better material better, but you haven't changed the weak link, and that's what fails first. And that's what the Corps of Engineers and the Bureau and Rec and everything they do now on locks and dams. Paducah, Kentucky has a lock and dam, a super lock that they're putting in down there now. It's a 6-year construction project. All the underwater concrete will be silica fume concrete, because you only want to do it once. You don't want to come back in 20 years and do any repairs. You want to do it one time and walk away from it.
How would you compare this to what we did with the Cooley Dam, I guess, was it? Used polymer concrete, the Cooley Dam.
For repair?
We had the same problem with the sluice gates, water coming in.
When was that done?
I guess it was done in 1975 something.
Okay, see this, since 83, the Bureau of Rec and Corps of Engineers have switched over to this technology. That would have been a preceding technology. Questions? Sure. Thanks, man. We talked about high strength and high rises and columns on bridges as one high performance concrete. In Seattle, all of the high rise buildings since 86, they used to be all steel, and since 86 on they're all concrete. And what they do in Seattle, I think, is pretty ingenious. I don't have any slides on it, but if you think of, that last slide we showed of reinforced concrete, this is what you typically see. Is that out of focus for you? No? Okay, it is for me. Typically you see the steel inside the concrete, inside the form, because concrete is good in compression, but not real good in tensile. Just the opposite, steel's real good in tensile, it's not real good in bending and flexural. So you combine those two properties together, you get a good column. What they've done in Seattle is, instead of putting the steel inside, they have hollow formwork, hollow tubes, round tubes, 8-foot diameter, no steel inside whatsoever, that go up through, well, you can see a couple of tire cranes here, that they literally pump the concrete into the bottom of these steel forms, fill up the steel form. There'll be one floor in height, and they put another one on top of it. So they'll be 8 to 12 feet high. They fill all the concrete up. The forms stay in place. So you've got this concrete column that's jacketed in steel. And you're going to put pressure on that concrete, and that's great, because the concrete's great in compression, but like a ball, if you press it, it wants a squeeze, and that's what happens when you break a cylinder. Did you ever break a concrete cylinder? Okay. When you squeeze a concrete cylinder, what happens is, if it fails right, you've got a cone on top of a cone. You've got a cone on top of a frustrum. What happens is this part in between blows out like a rubber ball. When you squeeze it down, this stuff expands and blows out. Well, if you put a steel jacket around that cylinder, How much weight could you push on that before that concrete breaks? I don't know that it would. I don't know. But that's how they're building their buildings, and they're starting to do this in New York City now for obvious reasons. But they found that it's more economical. They don't have to deal with all the rebar. They don't have to deal with all that extra steel. These are stay-in-place forms. You put this form in, you fill it up with concrete, it stays there. You don't have to take it back out, move it around, put it in another place. It's like an assembly line. The buildings just keep going up. Every building that they've built in Seattle since that time has been built with this technology, with filling up the steel casings. I think that's a great way. Let's look at some high-performance concrete mix designs. Here's one that's used in piles in North Carolina. Everything, in their case, in the Carolinas, they're getting all their aggressive chemical attack from the brackish water. So everything that's underwater, the concrete piles underwater, from here all the way up to the bottom of the bridge deck is all high-performance silica fume concrete. That's where they're going to get their chemical attack. They don't get freeze-thaw. They don't throw any salt on the top here like you do, like we do up north. They get all theirs from down here. So from here, from underwater all the way up to underneath this girder here, from here on down, is all high-performance concrete. And this is the mix design that they used. 624 cement, some fly ash, class F, and silica fume. We're talking about these two being pozzolan materials, Yeah, sorry.
And they still have to worry about all the sand and the salt coming off the water from the winds, getting on top and eroding it.
Yeah, but I think on the roadway, they're depending on a washing action from rain to wash that off, where whatever hits this side here, and what would spray and hit this may not get washed off.
That'd be 365 days a year.
Yeah.
I mean,
Yeah.
where we only put salt on for 3 months.
Yeah, excellent point. Good point. That's what they do. In Florida, they stop about halfway up. They stop at 20 feet above the water. I mean, it's the same. Why? Every state's different, the way they do things. But that is a good point. I know in parking garages, if you follow the American Concrete Institute for Designing Concrete Parking Garages, they say anything within I think it's a kilometer or 2 kilometers of the ocean, you should treat it as if it was, a parking garage here. It has the same salt attack. Well, what's the difference between a garage deck and a bridge deck? I mean, I'm supporting what you're saying. They should use it all if they're this close to the water. They do in the parking industry. Why don't you do it on bridges? I don't know. They're just slow in coming around. But in this case, in the Carolinas, they take it all the way up. In Florida, they actually stop here. They were looking for strength. In this case, besides low permeability, they were also looking for higher strength for load-bearing capabilities, so that's why they were pushing. This is typically twice as strong as what you would use if you were just looking for a lower permeable concrete. Here's one from New York DOT. Their actual mix, 500 pounds of cement, the same F-ash, some silica fume in there, and you see they're only making 5,000 psi. This permeability Coulomb number is a rating of the permeability of the concrete. A little bit different in mixes. You can see the goal, the difference in the water-cement ratio, lower for higher strength, more cement and silica fume for higher strength. If you're looking for permeability, you don't need strength. So you can take a lot of cement out. I've seen the lowest cement factor I've seen in Colorado. DOT actually has a high-performance mix design where they only use 390 pounds of cement per cubic yard, which if you go to Ferrier Brothers over here would probably blow their minds. They probably don't have a mix design over here that has less than 564 pounds of cement in any of their mixes. And they don't call it high performance, but yet in high performance, if you do it right, you mix the right materials together, you don't need that. And that's kind of the philosophy behind high performance concrete. Now that you've heard me talk for an hour or so, you all know high performance concrete philosophy. You all play poker and everything else. Tell me what that card is. Somebody.
Queen of Hearts.
Yeah, it's a Queen of Hearts. It's a Queen of Spades. I can't look at it either. I can say it without looking at it. If I look at it, I call it a heart too, but it's not. It's a queen of spades. And that's kind of what we're talking about with high performance concrete too. It's not the obvious. It actually means, if you use the technology, it actually means use the least amount of cement possible. Remember, we talked about the good actor and the bad actor in concrete. The aggregate's good, the mortar is bad. You want to use more aggregate and less mortar, but you want to make the mortar as good as you can possibly make it. Okay? So using cement alone only makes it a certain goodness, but if you add pozzolans to it, then you can convert more of that inefficient byproduct of cement water hydration into more cement. What you get is you get a particle packing if you're using silica fume and reduced permeability, ASR control with F-ash and silica fume. If you use less cement, you're able to use less water. And it's the amount of water in concrete that causes it to crack. You only need a certain amount of water in a yard of concrete to make concrete, roughly about 30 gallons of water. If you ever see any mix design that has more than 30 gallons of water per cubic yard, that extra water is only in there to make the concrete crack. And most people don't want their concrete to crack, so you don't need that extra water. So one way to control cracking is get rid of the water. Well, how do you get rid of the water? Get rid of the cement. We don't need all that cement in there anyhow, so everything is kind of following in line. Lower cement, lower heat of hydration. When cement and water reacts together, that produces the heat in the concrete. And if you have a differential temperature, like in those columns in New York, or in New York and Chicago, those columns, when they cast them, they may get up to 160 degrees temperature. If you have more than a 36-degree temperature difference between internal concrete and external, it'll crack, thermal shock, just because of that temperature difference. So what they do is they do two things. They try to make concrete that doesn't generate as much heat, and then they keep insulation blankets wrapped around those columns so that they can keep the heat in. It's only the shock of the outside coolness that will cause it to crack. And if you can keep it all warm and let it go up through its heat of hydration and come back to ambient temperatures in a week's time, you can take off those blankets and everything's fine. It's come back down to ambient temperature and you don't have that thermal shock anymore. But the idea of making concrete with low heat of hydration is good to help reduce cracking. Lower strength also helps to reduce cracking.
Talking about heating concrete, the hydration heat. They heat concrete and precast with concrete to cook it overnight.
Yes.
How would you reconcile the heating and non-heating argument? Here you want to keep the heating low, but in there they steam it.
In the case of the precast industry, they want to turn their forms every day. So you're working on a 24-hour schedule. If you're casting a beam, you know, the size of this, you want to cast it in a day, you want it to cook, and you want to be able to take it out of that beam and do the exact same thing tomorrow. And that beam has steel reinforcements and post-tensioning steel, and you're going to pull that steel and you're going to make a structural member out of this. The concrete has to achieve a certain strength before you can do all of those things. So the idea of heating in the precast yard is to try and get those, we said one of the characteristics you can do on high performance is get early age strengths. Precast would be that early age strength. They want 28-day strengths in one day so that they can turn that bed and make the same beam the next day, whether it's an I-beam or floors or something. But in the case of bridges or most other structures, it depends on the structure you're building. Heat of hydration comes into play when you're doing dams, big containment vessels, columns, where you've got big masses of concrete, feet thick. You know, in the case of some of the dams, the Hoover Dam is what, 60 feet, 200 feet thick at the base, some ungodly like that. I mean, it's just an amount of thickness. Well, it's that mass of concrete that holds in the heat. When they built the Hoover Dam, you guys have probably seen the video on the Discovery Channel, they actually had pipes, copper pipes running through the formwork that they actually pumped chilled water through, ice water, through the pipes. They poured the concrete on top of all these pipes. The pipes are still in place. They poured all these concrete on there. As the concrete gets hard, as the cement water hydrates, it's a chemical reaction. Most chemical reactions do something. They give off a gas or heat or something. Cement water happens to give off heat. Well, if it's surrounded by all this other concrete, it's a great insulation. That stuff gets really, really hot. And if it gets too hot, then it can crack. You don't want cracks in a dam. You know, it's to keep the water back, not to let it come through slowly. So they actually ran pipes through the mass concrete and ran cool water through it to try and control heat of hydration. That was way before, you know, this type of technology, but it's still done. Chilled water through concrete and mass structures, dams, Bureau Rec does quite a bit of that. But one of the reasons why we can do this, or how silica fume allows you to use the least amount of cement possible, is you get a replacement factor for it. Because of its size, its fineness, and its chemical reactivity, a small amount of it, in this case we're talking about you know, a 5 to 10% cement replacement, we can get as much as a 4 or 5, 6 times replacement factor, which means if you take out 100 pounds of cement, you can put in roughly 20 pounds of silica fume, 5-to-1 replacement, still get the same strengths. So you've gotten rid of some cement, you've gotten rid of all that water, and you've put a material in that can particle pack and do other things in the concrete, so silica fume really helps them to drive that cement factor lower and lower. This happens to be the Tollway, Illinois Tollway mix on the Chicago Skyway Bridge that was done 2 years ago, 03. This was actually their starting mix design with high cement factor, 665, some fly ash in there, no silica fume. The water, the gallons of water, this is the volume, absolute volume that mortar occupies. And you see what they ended up doing when they switched over to a high performance concrete. They took out almost 200 pounds of cement. Fly ash is approximately the same. They used silica fume here at 40 pounds. And if you think about it, this 40 pounds, we said that 5-to-1 cement replacement. They took out 200 pounds of cement and put in 40 pounds here. That's 5-to-1, basically. But when they did this, when they lowered the cementitious materials, they're only what, 470, 570, 610. 610 pounds of cementitious materials on this water here is only a 4:0 water cement ratio, almost a 4:1 water cement ratio. We talked about before low water cement ratios, those type things. Normally lower means better. In this case, their old mix was a lot lower water cement ratio than this mix was. In essence, you would think that this mix would not be as good following that technology, but what it shows was you're able to use more aggregate, larger quantities of the good material in your concrete, and strength-wise, well, permeability-wise first, the high performance is a lot less permeable, but strength-wise, we see that the materials catch up at 28 days, that the strengths are basically the same. 3 days, there's a little bit of lag here, but that's actually good for cracking on a bridge deck. When they ran this thing out to 56 days, this strength went up to over 6,500. So they're actually talking about taking more cement out of this because they don't need high strength concrete on a bridge deck. The bridge deck is designed for 4,000 PSI because when the trucks go over it, you want the bridge deck to do this. You want it to bounce and flex. If you make the deck too rigid, then it's not going to flex. So they actually are talking about actually getting rid of more cement out of this to make a lower strength concrete. In the case of Colorado, when they asked their ready mixers to supply a mix design, most people will give you a minimum. I want a 4,000 mix, I want a 5,000 mix, and you have to have a percentage of strength higher than that. In the case of Colorado, they say I want a mix design that's between 5,000 and 6,000 PSI. They cap you. You actually make a mix design that hits that number. They don't test you during the project, but as you submit your mix design for approvals for use on their structure, they make you hit this category. They know that extra strength is easy, but it brings a lot of other bad things to performance if you make too strong a deck. They want it to get as low as permeable as they can, but they also want it to be like regular concrete. From a construction standpoint, we've got a couple things that happen in concrete when we place it. And this is true for all concrete. We have various conditions on the surface of the concrete that cause drying. Sunlight, wind, wind's probably the worst. Humidity, moisture loss. There's always some type of evaporation going on, you know, just right here, right now. In concrete, with regular concrete, that's probably a good thing because regular concrete, when you place it, for you guys that have worked with concrete before, you know when you place it, when you strike it off, the first thing that happens is you get a bleed water that comes to the surface. You with me, the guys that work for concrete? What happens is that bleed water, when you place that fresh concrete, the concrete slowly settles, and as it settles, there's excess water in there. We said anything over, I should have stated that, anything over 30 gallons of water is all in there for cracking. You know, you really don't need it to make concrete. Here's our 30 gallons of water in the HPC. We've got an extra 7 gallons of water in there in the old mix. It's just all going to end up in cracking. But that excess water is not needed for hydration either. So what happens is as that concrete settles, this excess water comes to the surface on conventional concrete, and you have to let that water evaporate off the surface before you close the surface and do your final texturing. If you were to just place that concrete, conventional concrete, and close the surface and start curing it and do everything that we saw in that video, you would seal all that bleed water into the concrete and trap it under the surface. That's what a lot of contractors get into trouble with when they do sidewalks and people's driveways. They place concrete and the very next winter, the whole top of the concrete is scaled off. And the owner's freaking because he spent $10,000 for a concrete driveway supposed to last for 20 years and it came off in one winter. What happened is the contractor didn't let the bleed water come up and evaporate. He sealed that bleed water in the deck. When the bleed water came up, it couldn't come up and evaporate, so it made for a very weak surface in that concrete. When it went through freeze thaw, bam. You know, when water freezes, it expands 9%. That expansion creates a real lot of tensile force in concrete, and we said concrete's not good at tensile. So it fails in freeze thaw very quickly. That's conventional concrete where there's some bleed water. In the case of high performance concrete, this is where the difference starts to show up, and we probably saw it in some of the videos, is the concrete looked gooey, it looked sticky. There wasn't a lot of, no bleed water, you know, because this silica fume has filled up all that void spaces between those baseballs with its BBs. So there's actually no excess capillary pores for the water to migrate to the surface. So on high performance concretes, normally there's no bleed water. Guys have finished concrete their whole life. You know, this is the only way they know how to finish it. You place it, you strike it off, let the bleed water go, we come over, have a cup of coffee, a sandwich, go back an hour later and finish the concrete. You can't do that now. High performance concrete doesn't have bleed water on the surface. So if there's no bleed water on the surface to protect the surface from drying, evaporation doesn't know that. Evaporation's still drying the surface out. Well, once it dries out to a certain point, it cracks. It's called plastic shrinkage cracks. ACI says plastic shrinkage cracks. What is it? By definition, it's cracking that occurs in the surface of fresh concrete soon after it's placed or while it's still plastic. Two key things. Fresh concrete, still plastic. Fresh concrete means when the time the concrete comes down out of the truck, it's fresh, it's movable, it's plastic. It only stays plastic for about 3 hours until it sets. The cement water hydration chemistry makes it start getting hard. So plastic shrinkage cracking only happens in that first 3-hour window. If you can start developing strength in that concrete, you won't have plastic shrinkage cracking because it only happens while it's still stiff and still fresh. So we've got this 3-hour window that we need to protect the concrete from surface drying, but the concrete doesn't bleed, so why do we have to wait for 3 hours? If it doesn't bleed, let's just finish it sooner. Well, let's cure it sooner. If we can cure it in 10 minutes time, then who cares how long plastic shrinkage may be in effect? We have it protected from drying. And that's kind of the way that the finishers have found. This is a chart that's also found in the book looking at finishing parking structures. I'm not going to spend time on this. That'll take you through if you need it. One of the ways to work with contractors on placing high performance concrete with silica fume without bleed water is, you know, you and I, we can stand here and be real didactic. I can tell you information and you can understand it and you can learn. Some people can learn by see-do, like little kids. You show them something or follow me and, you know, they do it right away. Ride a bike, skiing, anything like that. They're good at see-do. Contractors, you're not going to tell them how to finish concrete and you're not going to show them because they've been doing this for 30, 50 years and they know how to do it, right? Even though they may be doing it the way they do with conventional concrete, not for high performance concrete, how do you get them to learn that? And the way to do that is it's called guided discovery. I'll let you discover what I wanted to tell you in the first place, but I'll just guide you so that you discover what I wanted to tell you. You wouldn't have listened to me if I told you anyhow, so we'll go out and do a test pour for never-evers, people that have never ever worked, contractors that have never ever worked with high performance concrete before. A lot of specifications will actually require a test pour. And the engineer and the architect and the owner will come out and actually stand around and watch the test pour, watch everything happen, you know, watch the contractor do his thing. But what happens is as the contractor's doing this test pour, he sees certain things. This is part of his guided discovery. He sees that, hey, this concrete, it's not as slumpy. You know, even though it said it was a 7-inch slump here, this stuff kind of sticks together really well. It's not as slumpy as what it normally should have been. They pick up right away the fact that the concrete doesn't bleed. You strike it off and there's no sheen on the surface of the concrete. So in various conditions, you actually leave part of the test slab out. Let it go bad. It's a test slab. Let them fail. Let them see what happens if you don't do the right thing. Another way for them to learn. So there's part of this test slab. We won't do anything to. We'll let them finish it the way they would normally finish concrete, just so they can learn themselves what works and what doesn't. Once they learn that this has this plastic shrinkage cracking or potential, then they get into all these elaborate evaporative protection schemes. If you go to American Concrete Institute, they have a whole list of different things you can do, from windbreaks, you know, erecting a windbreak to stop evaporation, wind screens. They go into elaborate fogging, actually fogging, supposedly putting a mist in the surface, trying to create a higher humidity above the bridge deck to stop, you know, this from happening, you know, the evaporation from happening. They go to great stretches of describing, you know, what to do to try and stop evaporation. It's nature. You can't stop evaporation. Deal with it. And that's what we're talking about here. Deal with it. There's no bleed water. If you can place the concrete and you can close the concrete surface, you don't have to worry about trapping any bleed water. Go ahead and do that. You want a final texture? You want a broom texture? You want a tine texture? Fine, put it on and then begin your curing right away, right behind it. If you start curing right away, whether it's that white pigmented curing compound that we saw in the video, or whether it's cotton mats or wet burlap, start putting that on the concrete right away. 10 to 15 minutes after it's been placed, it's already under wet burlap, or it's already under curing compound. It's already done. It's done, guys. Go home. Contractors, leave all your tools on the truck. All your hand tools, all those extra tools for working the concrete and rubbing it and making it look good. They hate when I say this, and ready mixers love it, but the concrete coming down the chute of that truck is as good as it gets. There's nothing the contractor can do to make it any better from a durability standpoint than taking it out of that truck and doing whatever he has to do with it to build the structure and get away from it. The more you work the surface, the lower durable the concrete will be. So what we're talking about here is no delay in final finishing and fast tracking. If you've ever seen them pave a highway, they pave a highway with very stiff concrete. They slip form it. They feed concrete out here. It's like Play-Doh, and the machine walks along and the pavement comes out of the back end of the machine. 200 yards down the road, they'll have a curing train, another bridge that comes across, and they're spraying it with curing compounds. So the finishes are all stretched out within that 200 yards. Well, that's on a normal highway. All we've done for bridge decks and with high performance concrete is we've condensed that train. Instead of being 200 yards long, we've condensed it down to about 30, where the concrete's placed, consolidated, surface is closed, textured, and curing begins, and everybody moves down the pavement all at the same time. You get down at the end of the pavement, everybody goes home. We don't have to stay around 3 hours and wait for the bleed water to bleed and get out there and final finish it. It's fast tracking. It's this type. Guys aren't used to that. These finishers are used to being around there till 8 o'clock at night finishing concrete that they should have been off of at 3. But that's what they do. It's a hard lesson for them to break. You guys can be the change demons. Make things change. I use this photograph because when you ask for a test pour, this is what normally happens. The ready mixer gets a great slab in his yard, but this is a test slab for a bridge deck. And a couple things here. These aren't the finishers. These are the superintendents that are going to be there. So these aren't the guys that are actually going to finish the concrete anyhow. Secondly, this isn't the equipment. They're not going to place the concrete on a bridge with a 2x4. They're going to use a big bidwell paver, sophisticated equipment, all this stuff. They're not going to use a broom to texture it. They're going to have it tied onto the bidwell. And they're not going to hand finish it. So the only thing this is really accomplishing is they're seeing that there's no bleed water. You see there's no sheen on this concrete. There's no water on the surface of this concrete. So they're placing it finishing it, texturing it, curing it, go home. 10 minutes. If you do it right. On a parking deck, this happens to be in Milwaukee Airport. This is slab on grade. They used the slab on grade as a test pour. Before they got up on the decks, they figured if they're going to make a mistake, we'll do it on grade where we can yank it back out. But you still, they used the bridge screed here, they used the paving screed here, where that was used to be over here, they're bringing it over here now. Right behind the screed, they're hitting it with a float to close the surface. The float actually has a broom off the front of it, which I think I have another video of, or a picture of. And then spraying it with curing compound. This white pigmented curing compound is just that. It forms, it's a liquid that when it dries on the surface of the concrete, it forms a film that you can actually kind of pick off as a sheet. It almost forms like a rubbery film on the surface of concrete to keep the moisture in the concrete from evaporating. This is another shot of a finishing of a parking deck. Indianapolis Airport is building a 6,000 car parking deck starting next month. Silica fume concrete is in the specification. All these videos and user manuals and everything the local contractors are all going through right at this time to learn this technique, where they place it, close the surface, texture it, cure it. They're pouring it off in strips. You can see how they're going. You can see the individual strips going across the deck. Once they get down to the end of the deck, they're done. It's being finished and cured right here. They never have to get back onto this. Even though you can't walk on this concrete, it's still considered fresh. Where old way of finishing, you'd still get on this concrete and work it later on. This stuff is still fresh, but it's done. It's finished. There's nothing less to do with it. This is the, here's the broom. They actually invented a tool when we first started because of the non-bleeding concrete here. You can see there's no shine on this concrete. They use a tool which is called a Fresno. It's a steel trowel. A lot of guys that work with concrete, they use a lot of wooden tools, wooden floats, bull floats, wooden floats. Really good for consolidating aggregate and that type of things with conventional concrete. But because this stuff is real tacky, wood float will just kind of pull and tug at the surface. Instead of closing the surface, it'll actually rip the surface back open again. This concrete without the bleed water is very sticky. It's cohesive and adhesive. It'll stick to everything and it'll stick to itself. So if you start pulling it, it'll have a tendency to want to rip apart. So they have to close the surface, and they do that with this steel trowel, which works very well, and then they have to put a texture on it. Well, you know, if I'm going to try and reach out there with the broom and put a broom texture on, it's crazy because you can't balance it 30 feet out without it smacking into the concrete. The guy says, I'll just attach, and the contractor actually made this, he just attached the broom off the front of his Fresno. So when he actually pushes this tool out across the concrete, this edge of the blade is in contact. Everything is tilted this way. This actually rides in the air. As he's pushing the bull float out across the deck, the broom rides in the air. When it gets to its furthest point, he turns what's called a hustler joint right here, which changes the angle of the blade from this angle to this angle, thereby lowering the broom onto the deck, and he pulls it back towards him. He not only closes the surface, but he puts a texture on at the same time. 2 steps in one. The next guy sprays it with curing compound, they go home. Without the curing compound or without curing immediately, this will crack. It's like, give me a piece of paper and let me guarantee you that it will crack now so that I don't get the phone call. If you don't cure it, it's going to crack. Because there's no bleed water here. I mean, it's physics. You know, it's going to crack if you don't do the right steps. Some of the things that they found in the part of what's doing the right steps is if you can, particularly on bridges, they're placing them more at night. Less traffic at night. It's safer at night without traffic on the highways. But it's also a lower temperature at night. And we talked about this temperature differential. If you think about placing concrete in the morning, if you place concrete at 8 o'clock in the morning, it's probably going to sit around for 16 hours before it really starts gaining temperature. So at about 24 hours, 22 hours or so, it'll be really peaking at temperature. Well, 20 hours from 8 o'clock in the morning is 4 in the morning. So your concrete's going to be getting its hottest when it's the coldest outside. It doesn't make sense. You've got the concrete gaining temperature at the same time that your environment out here is losing temperature. If you place concrete at night, 6, 7, 8 o'clock at night, what happens is It starts getting hot 3 o'clock in the afternoon, 4 o'clock in the afternoon, 5 o'clock in the afternoon. Well, that's fine. That's the hot part of the day. So everything climbs together. It's not the fact that the concrete gets hot. It's this coefficient. It's this difference in temperatures between the outside temperature and the concrete temperature that'll cause cracking. So they place a lot of bridges at nighttime. Lower temperatures at night, reduced temperature differentials. They have a tendency to place it as the lowest slump possible. If you place, slump is that on the video where they pulled that cone up and the concrete all fell and they measure how much slump that is. When you have a very high slump concrete and you're pouring it over steel, what happens is sometimes is that concrete, because it has so much flow, will have a tendency to start to settle over the reinforcing bars. And the reinforcing bars will act as stress risers and actually cause the concrete to crack as it settles around the reinforcing steel. So if you take some of that slump out of the concrete and it can support itself out, lower slumps are better for reduced cracking. This stuff, you can't over vibrate it. It won't segregate. And as we said before, early finishing was better than excessive hand finishing. All the curing practices that have been found to date is they immediately cure it with water, at least for 7 days, wet burlap, those type structures. When you're doing multiple bridges, multiple long span bridges, normally what happens is if you have a single span bridge, you have one column here, one column here, we're going to cross the interstate, we're going to go in one continuous span. They'll start pavement on this side and just go in one complete motion all the way until they're on the other side of the deck. If you're doing viaducts, or like up on 294 in Chicago, where you have these long continuous spans, maybe a mile long, over, not even over a river, over somebody's backyard, just elevated, it's a bridge. But what happens is you can't place those from one end to the other end straight through. Because as you're placing the concrete on the bridge, while the concrete is still fresh, it has a lot of weight. It's liquid almost, so it has a lot of weight on the surface, and you're deflecting that. It doesn't have any strength-bearing characteristics because it hasn't gotten hard yet, so it can't support itself, so it adds a lot of weight to the structure. So what happens is when you build multiple span bridges is you have to place all the positive moment regions first. You have to place all those regions over top of the columns first, and then you come back the next day and you do the negative moment regions, because of that weight loading. If you were to do the one continuous pour straight through, this extra weight on this 3rd or 4th segment would be cracking this concrete all the way back here just because of the extra weight tilting the bridge. And this concrete back here is not hard enough to support its own weight yet. So there's a little bit different construction practice when you're doing excessively long bridges on placements. If they have the technique worked out well, this is what it looks like in a snapshot. The Bidwell pavers up here with the epoxy-coated bar. They're putting a texture on this concrete here. They're placing it in the evening. You can see by the sunlight hours. And the wet burlap is probably 10 minutes maybe behind. No bleed water. I actually don't like this concrete. The guys that they're using an AstroTurf drag, a piece of AstroTurf wrapped around a bull float. And this guy on the catwalk here just drug it across this whole deck. You can see there's some rattiness that's been rolled up on the surface. They actually had polypropylene fibers in this concrete to try and help with plastic shrinkage cracking. I said there's 1,001 things you can do to control plastic shrinkage cracking. They really didn't need the plastic fibers if they're going to cure it this quickly, but they still had it in there. But what happens is that all those little fibers from the AstroTurf grab onto the mortar, and the mortar is real sticky, so it sticks to the fibers and it sticks to itself. So the more you use it, the more mortar it pulls off the concrete, and the real rattier the surface becomes. But the district engineer in this particular case, they like it this rough. You drive your car across it and you can definitely tell there's a different texture on the bridge that has got a whole different zing to it. This is some of what they do also. I see engineers that go into great detail. Oh, plastic shrinkage cracks. We got to stop plastic shrinkage cracking. I have to fog the concrete. I have to create this humidity. So they go to great extents of putting in elaborate fogging machines and spending money. It's wasted. It's wasted. First place, you're not supposed to spray the water down directly onto the surface of the concrete. It's supposed to be raising the humidity of the air above the concrete. You might as well just get a garden hose and spray it on the concrete. Secondly is, if they were prepared to put the curing on, they don't have to texture this. They're going to come back and saw cut it later. If the contractor was prepared to put the wet burlap on this close to the paver, what good's this doing? He already has it under cure. This is useless. He just spent all that extra money to do nothing. I mean, if he did the right thing first, which is what he's doing, he doesn't need the fogging machine. Plus, he's placing it in the morning. But he's got the cure on right away, so that's good. People spend so much money on fogging, and it just doesn't, I mean, if you can place it and finish it, and here again you see it, you know, the bidwell's placing it, this guy's texturing it, here's the wet burlap under there, it's 10, 15 minutes behind. There's not a fire drill going on here. The guys aren't overworking. There's this is an easier job all around. I don't like tools that stick to the surface. We said that wooden tools will stick and tug at the surface of silica fume concrete. Steel tools work best. This is what a texture looked like. People say, well, if I put a texture on, in this case you can see the astroturf, the green up here. If I put a texture on here, when I lay this burlap on, isn't it going to smash down all the texture? And no, not really. I mean, the guys that say that have never been out on a bridge deck, because normally what happens is, you know, he's got one end of the burlap and I have the other end here. We pick it up, we lay it down on the deck. We don't drag it across the deck. We're not dragging it across. We're laying it down across the deck. So it's just the weight resting on the concrete. Here's tined concrete that had wet burlap applied, as was in the other picture, literally minutes behind. The wet burlap doesn't smash the tines out. Yes? Good. I think we're close to the end anyhow.
Question to Tony. You see how rich the presentation is and concrete. Some of you think that I like concrete. You see why. Any questions for Tony?
Oh, thanks. If you need to reach me when you're out there working your jobs on anything that has to do with concrete, it's my name, Tony at silicafume.org. Real easy. Silica Fume's all one word. The other class took all my business cards, so I'm sorry. It's just my name, Tony at silicafume.org, O-R-G. Thanks, guys. Have a great week.